Okay, so good evening, everyone. Can you hear me? Yes?
Yes.
So, let me just start off. Okay, so let me just start off very quickly by answering a few questions. So I received a few questions from last week's, or not last week, but from the BJT set of lecture notes. So let me just very quickly go over that before moving on to today's intended lectures. So one of your colleagues asked about this base Gamma number, and they were asking about the intrinsic carrier concentration in the base as well as the intrinsic carrier concentration in general. And your colleague asked whether they should be the same or so. In some situations, as you know, the base might be made up of a material that can have a different, that could be different from, let's say, silicon. And as a result, it would have an intrinsic carrier concentration that would be different from, let's say, the intrinsic carrier concentration of silicon. So as a result, this is why there are these two notations. So Ni corresponds to the intrinsic carrier concentration. And remember, what is the difference between intrinsic and extrinsic? So intrinsic, this means this is a material that is pure. There are no dopants that have been introduced into this material. And so it's been made, or it's been turned into an extrinsic material. But as I mentioned in the previous lecture, you won't necessarily need to know what the base Gamma number is. You won't need to solve or calculate what the base Gamma number is. So that is just a brief explanation why there is NIB and why there is NI in this particular expression. So NIB corresponds to the intrinsic carrier concentration in the base, which can be different from the intrinsic carrier concentration in a particular material. Let's say it is silicon. Then there was another question regarding the solved example. So there was a question over here. I believe it was here in this particular example, where I was discussing how to calculate the width of the depletion region in this case. And as far as I remember, I mentioned that the width of the depletion region is equal to the square root of 2 times epsilon naught epsilon r over q n d multiplied by VBI. And your colleague had asked why I had used this simple notation, why I have used this simple notation. So I use this simplified notation as a result of the fact that this is a P plus N junction. So in this case, the acceptor carrier concentration is much, much larger than the dopant carrier concentration. So in this case, the depletion region is going to extend further in the... So if this is a P-N junction, and we know that here this is P is much more heavily doped in comparison to the N. So if we were to have a depletion region, where would the depletion region is going to extend further towards which side more? So I guess it would extend more towards the N side. There'll be a smaller depletion region on the P side, but there'll be a larger depletion region on the N side. Now, this does not mean that we ignore the width of the depletion region in the P side. Absolutely not. We do not assume that it is 0. Okay, so we don't say that XP equals 0. No, never. Okay, so XP is not equal to 0. XP is just very small. Okay, XP is just very small, and for this reason, we just want to calculate what is the total width of the depletion region, but because XP is very, very small, XP is very small, so therefore we say that W is approximately equal to Xn. So W is approximately equal to Xn. Why? Because the width of the depletion region in the N-type is much, much larger in the N material. in the n-type material. If you are not comfortable with this shorthand notation, please use the full expression. If you are not comfortable with this shorthand notation, then use the full expression for the width of the depletion region. Okay, so I believe the full expression is a square root of 2 epsilon naught epsilon r over q times 1 over na plus 1 over nd times vbi. So if you are not comfortable with using this shorthand notation, this is okay. This is perfectly fine. Okay, both are exactly both. You will not be penalized in any way. And just to further reinforce this piece of information, if you look at this example that I recommended for you to do, this example over here, and I really recommend that you go through this worked example. There is a very high chance that there could be a BJT question in your exam, either the main or the reset exam. So it is really worth going through this example. And as you can see over here, if you go through this example, so this is an NPN. So this is an NPN transistor. And in this case, the emitter doping, 2 times 10 to the 18, is much, much larger than the base doping. So the emitter, so this is ND, is much, much larger than the base doping, so Na is 10 to the 16. So as a result over here, when we are calculating the width of the depletion region between the emitter and the base, see, as you can see here, so we have used Na. We have used Na, okay? We have used Na. So this is opposite to the previous example, where Na was much larger than Nd, and as a result, we had to use Nd. Okay. So whoever had asked that question, I hope this answers your question over here. So we don't obviously, so number one, we never assume that the width of the depletion region is going to be 0, never, but this is just a way to simplify how to calculate the width of the depletion region due to the fact that there is this asymmetry in the doping concentrations on either side of the PN junction. So this applies to a BJT or a PN junction diode. Okay, and as you know, a BJT has 2 PN junction diodes. Okay. So again, I strongly encourage you to go through this worked example. I strongly encourage you to go through this worked example. Now, today's lecture, we will look at field effect transistors. But before I do go through today's lecture, for next week's set of lectures, we have 2 lectures next week. Please remember to bring a connected device. So for next week's lecture, please remember to bring a connected device. Why? Because we will trial the use of Padlets. Have you used Padlets before? Okay, Padlets. So we will trial the use of Padlets next week. So on Monday's lecture, please remember to bring a connected device. So I'll write it here. Monday lecture. Bring a connected device. So connected means connected to the internet. Okay, so for Monday's lecture, please bring a connected device. Remember this so that we can take part in the lecture together. Okay, so moving on. What is a field effect transistor? So in today's lecture, we will look at junction field effect transistor. Hello, can you hear me? Hello, can you hear me? Okay, very good. So as I was mentioning, the purpose of today's lecture is to go through junction field effect transistors. So there are two types of transistors. There is the N-channel and there is also the P-channel transistor. So the N-channel transistor means that in between, so the N-channel transistor means that in between the terminals of the p-type material, there is an n-channel. The n-channel is responsible for current conduction. So JFETs, they're also very similar to BJTs in the fact that they are also three-terminal devices. So what we have is a gate, a drain, and a source. Okay, we have a gate and a source. So in this case, this is an n-channel. Why? Because there is current that flows between the drain and the source, and the current that flows between the drain and the source in this case takes place inside an n-type material, which is why it's called an n-channel. A p-channel would be the opposite. So in this case, we would have current flowing in a p-type material. And similar to a BJT as well, in addition to the fact that it is a three-terminal device, in addition to that, we also have two PN junctions. So as you can see, we have a PN junction here, as well as another PN junction here. So similar to a BJT, this also has two PN junctions. The main difference, though, between BJTs and JFETs is the fact that a JFET is a voltage controlled device, whereas a BJT is a current controlled device. Okay, so the main difference between the JFET and the BJT is that the BJT is a current controlled device, as you have seen. What happens when we apply a IB current, and the fact that increasing the IB current results in an increase in the collector current. Okay. Whereas in the JFET, this is opposite. What we have is a voltage control device. Here is a schematic representation of our JFET. So VGS, so the voltage between the gate and the source, is equal to VGD, the voltage between the gate and the drain, plus VDS, the voltage between the drain and the source. Okay. So here are some schematic representations of a JFET. So we will continue, we would use this simplified representation of a JFET. In practice or in reality, this is what an N-channel JFET looks like. So as you can see, all three terminals, the source, the gate, and the drain, they are all placed on the surface of the transistor. Okay, this is what happens in reality. However, for the purpose of our lectures, we will use this simplified structure, this basic simplified structure to explain how a JFET works. And we will focus mainly on the N-channel JFET. So here what we have is, we have metallic contacts at the top. So the gate consists of these two metallic contacts. And then beneath these metallic contacts, we have a p-type material. So in this case, it has an acceptor carrier concentration that is much higher than the dopant carrier concentration in the n-type material. In the basic equilibrium, when there is no voltage that is applied between the gate and the source, we have a depletion region that is being generated. So this yellow area is a depletion region, as you know. Once we place an n-type material in contact with a p-type material, we get this depletion region. The depletion region prevents the further movement of majority carriers in the junction between the two types of materials. Okay, and here, over here, what we see is this cross-sectional view. So here we have this cross-sectional view. This cross-sectional view is important because it will help us understand how carriers are going to move inside this channel, and what also happens to the width of these depletion regions between the gate and the source and the drain. Okay. So in reality, as we discussed, the terminals of the gate and the source and the drain, they are all placed on the surface of the transistor. These three contacts, the gate or these three terminals, the gate, the source, and the drain, they are usually made out of metal. There is an insulating layer that is placed. This is usually silicon dioxide, an insulating layer that is placed between each of these metallic contacts and the semiconducting materials. And we will discuss the importance of these insulating layers when we discuss MOSFETs later on. Okay. So here we discussed, here we just mentioned what happens in equilibrium conditions. In equilibrium, when there is no voltage applied between the gate and the source, and there's also no voltage applied between the drain and the source. Now, what happens when we start to apply some voltages? So let's begin with a VGS of 0. So there's no voltage applied between the gate and the source, but we start to increase the voltage or the potential between the drain and the source. So we are connecting our device in this way so that the positive terminal of this battery is connected to the drain, the negative terminal is connected to the source. And if we look at the potential difference between these 2 points, between point A and point B, because we have connected the positive terminal of our battery or of our source to the drain in this way, then the potential at B is going to be much larger than the potential at A. In fact, the potential at A, or the voltage at A, is going to be very close to 0. The potential at B is going to be VDS. So whatever voltage that we apply, this point here is going to have a voltage of 1. This is going to have a voltage of 0. And in between these points, these 2 points, there is this variation in the channel voltage. So in between points A and B, or locations A and B, there is going to be this difference, or this voltage in the channel. And it's not going to be a linear relationship. This is because we have a material which also behaves in a nonlinear fashion. Now, let us assume hypothetically what happens in this particular material. So as VDS is equal to 1, so we have 1 volt over here, and we start to have a current that flows between the drain and the source. We have a current that starts to flow between the drain and the source. And this current, let's assume that it is 6 milliamps. So ID in this case is 6 milliamps. Now notice what happens. Notice what happens as we start to increase VDS. As we have just mentioned, because the potential difference, or because of the fact that at point B, the voltage is much larger, or is large in comparison to A. A here, the voltage is equal to 0. And then what have we done? What have we done as a result? What have we done in this case, in this region here? So I believe what happens is we have a reverse bias. We have, in this case, this region is more reverse biased, right? Because this terminal is positive. This is an N channel. So we have reverse biased this region. What we have done is we have reverse biased this region. And what happens when we reverse bias a PN junction? What happens when we reverse bias a PN junction? What happens to the widths of the depletion region as a result of reverse biasing a junction? Does it increase or decrease? What happens to the width of the depletion region as a result of reverse biasing? Does it increase or decrease? So I think it increases, okay? As a result of reverse biasing, the width of the depletion region increases. And this is exactly what's happening in our JFET. So in this region of the JFET, as you can see, the width of the depletion region, in this area, is now starting to increase. So the width of the depletion region in this region is starting to increase. This is still the same. Okay, that's fine. So there's now a narrowing of this channel near point B. There's a narrowing of this channel near point B. If we continue to increase VDS, now if we continue to increase VDS from 1 volt to 5 volts now, look at what happens in the depletion regions. Now both the depletion regions are now touching each other. This is known as the pinch-off point. This is known as the pinch-off point. Okay, so at this point, the point at which both depletion regions touch each other, this voltage is also known as the pinch-off voltage. So when increasing VDS to the point at which both depletion regions touch each other, this is known as the pinch-off voltage. So VDS is equal to VP, and this is known as the pinch-off voltage. Now, the current, as you can see now, has increased from 6 milliamps. So the current between the drain and the source, it's increased from 6 milliamps to 10 milliamps. But what happens when we continue to increase the voltage, VDS? Now, doubling the voltage from 5 volts to 10 volts, notice what happens here. The position of the pinch-off point has just shifted slightly. So the position of the pinch-off point has shifted slightly. It is now here. But because the channel has now been completely sealed, it is now difficult for current to pass through this channel. The channel is now completely blocked. So as a result, the current is very small. So the drain current in this case is very small. So it's increased despite the fact that we've doubled the voltage from 5 volts to 10 volts. Notice what happened to the drain current. It has increased from 10 milliamps to 10.1 milliamps. So there's been a very minor increase in the drain current beyond the pinch-off point. So in actual fact, if we were now to plot the ID versus VDS curve for this particular JFET, see, ID versus VDS curve for this particular JFET, this is the behavior that we would notice. So just to recap, keeping first of all, VGS is equal to 0. So here we are assuming that VGS is still equal to 0. But gradually increasing VDS results in a reverse bias in this region of our JFET, which means that the depletion regions are starting to touch each other. We notice that there is an increase in the drain current. This increase in the drain current is non-linear until we reach the pinch-off point, until both depletion regions touch each other. And here what we have done is we have reached the pinch-off voltage. So this is the pinch-off voltage, VP. So this is called VDS SAT. So this is the drain source voltage at which saturation begins. Beyond this VDS, so at VDS greater than VDS SAT, this is known as the saturation region. So this is known as the saturation region. And in an ideal JFET, there should be no further increase in the drain current in an ideal JFET. But in practice, obviously, this doesn't happen. This is similar to a BJT when we have base width modulation, right? So this is similar to a BJT. When we further reverse bias the base collector region, in theory, this should result in no further increase in the collector current, but in practice there is a slight increase in the collector current as a result of base width modulation. So similarly, in a JFET, in an ideal JFET, there should be no further increase in the drain current. However, there is a slight increase in the drain current, and we shall see why in the next slide. So in practice, however, what we do find is that there is a very slight increase in the drain current. So again, assuming VGS is 0, but VDS now has been increased or has reached VP, the pinch-off voltage, 5 volts, now doubling the drain source voltage to 10 volts, we said that the channel is now completely pinched off, but further increasing this VDS results in a shift in the pinch-off point. But as a result of this, what we have created here is an electric field. So here now there is an electric field. And similar to a BJT, when we continue to increase the voltage between the base and the collector, this reverse bias voltage increases the strength of the electric field. And by increasing the strength of this electric field, we are able to draw, we are able to attract, we are able to pull more electrons. So it's the same over here. This electric field becomes much stronger as a result of increasing VDS, and this electric field is now able to attract, it is able to pull more carriers, and because of this electric field, this is why we are seeing this very small but noticeable increase in the drain current. Okay. So VDS is increased to a value that allows the two depletion layers to just touch when VDS is equal to VP, that is in this case 5 volts, when the P plus N junction voltage at the drain end. So this pinch-off voltage is given as a negative voltage, okay? When VDS is very large, so VDS is much greater than the pinch-off voltage, so that the short length of the channel is now pinched off, but further increasing this VDS voltage results, as I mentioned, in a slight increase in the drain current as a result of this electric field being present. So what we have is we have these two main regions in the JFET. So we have this nonlinear behavior taking place over here, just before a pinch-off or just before VDS sat. And we have this over here, we have the saturation region. Okay, so we have two main regions, the saturation region as well as the nonlinear region in the JFET. So here is some further explanation to what happens just beyond pinch-off. So here are some further explanations to what happens beyond pinch-off. So that means when VDS is much greater than when VGS is much greater than the pinch-off voltage VP. And as I've just discussed with you, so the electrons in the N channel, they drift towards the point P. When they arrive at P, they are swept across the pinched-off channel by an E field. This process is similar to minority carriers in the base of a BJT. Okay, so this is very similar to the case of a BJT as a result of increasing the reverse bias voltage, which increases our strength of the electric field. And obviously, this channel, it has a resistance. So the resistance of this channel is usually denoted in terms of RAP. So RAP, so this is the resistance between points A and P. And this resistance is obviously changing as a result of the VDS voltage that we are applying. So increasing VDS, as a result of increasing VDS, most of any additional voltage simply drops across this region over here. So we've called this LPO. So any extra voltage beyond the pinch-off voltage is simply dropped across LPO, and this region is depleted of any carriers, and as a result, this is also highly resistive, okay, because it is depleted of any carriers. So here's an explanation of what happens in our JFET. So here is a brief explanation to what happens in our JFET. So we said that the behavior of the JFET when VGS is equal to 0. So all this relies on the fact that VGS is equal to 0. We shall see in a moment what happens when we start to increase VGS. So the resistance between the source and the drain is the resistance of the conducting N channel between points A and B. When a positive voltage is applied to D with respect to S, so VDS is greater than 0, so we start to have a current flowing between the drain and the source, which is equal to the drain current ID. There is a voltage drop along the channel between points A and B. The voltage in the channel is 0 at A, and it is VDS at B. So because of the fact that there is this potential difference between points A and B, then what happens is we are reverse biasing one of the regions. So as the voltage along the channel is positive, the PN junctions between the gates and the N channel become more reverse biased from A to B. So the depletion layers extend more into the channel and thereby decrease the thickness of the conducting channel between A and B. So because we are increasing this reverse bias, we are increasing the width of the depletion region, and we are decreasing the thickness of the channel, of the conducting channel from A to B. Increasing VDS further results in an increase in the width of the depletion layers, which penetrate more into the channel, and they result in more channel narrowing towards the drain. The resistance of the N channel RAB therefore increases with VDS. Okay, so the drain current therefore does not increase linearly with VDS. So this is all when VGS is equal to 0. Now let's see what happens when VGS is now changed. Now if you remember with our BJT, what happens when we increase IB? So when we looked at the IC versus, when we looked at the IV characteristics of a BJT, when we increase IB, we find that the collector current IC also increases. Now, what happens when we change VGS? First of all, we assume that VGS was equal to 0. Now, let us see what happens when VGS is varied. So let's start off with VGS is equal to minus 2 volts. Let us see what happens when VGS is minus 2 volts and VDS is equal to 0. Immediately what we notice is that the width of the depletion region is much larger. So compare the width of the depletion region in this case for this device with the similar device when VGS is equal to 0. You'll find that the depletion region starts off very narrow and the channel itself is wide. Here immediately, before doing anything, when VGS is minus 2 volts, we immediately see that the width of the depletion region is large, and the width of the channel between the drain and the source is narrow. Now, when VGS is minus 2 volts, but we start to increase VDS. So now we've increased it to 1 volt. There is now some current that is flowing between the drain and the source. As we discussed, the width of the depletion region in this area that is closest towards the drain, they start to become closer together, and there is this narrowing in the channel. This narrowing in the channel, if we continue to increase VDS further, we still have some increase in the drain current, but now these two depletion regions, they touch each other. Now the width of these two depletion regions, they touch each other, and what we have achieved is pinch off. What we have achieved is pinch off. So immediately, when we have a negative VGS bias, we start off with a narrower N channels at the start. So compared to VGS is equal to 0, the same VDS, see, the same VDS gives less ID as the channel is narrow. So compare, in this case, VDS ID is equal to 1.8 milliamps, whereas in our previous example, when we had VDS is equal to 1 volt, ID was 6 milliamps. So when VGS was 0 and VDS was 1 volt, ID was 6 milliamps. In this case, when VGS is minus 2 volts and VDS is 1 volt, notice what happened to the drain current. It has significantly dropped from 6 milliamps to 1.8 milliamps. Notice also what happens to the drain current when VDS is 3 volts. In the past, if you remember, pinch off was achieved at 5 volts. So when VGS VP was 5 volts. In this case, when VGS equals minus 2 volts, VP equals 3 volts. Okay, so notice the relationship in this case. So VDS is equal to VGS plus VP. VDS SAT is equal to, VDS is equal to VGS minus VDS. So VDS is equal to VGS minus VDS. But the VDS SAT is equal to, so the saturation voltage is VGS plus VP, right? Why? Because VP is a negative voltage. So in this case, a smaller voltage is required for pinch off. So instead of pinch off taking place at 5 volts, now pinch off occurs at a much smaller voltage at only 3 volts. So the channel is pinched off at VDS is 3 volts. So this is sooner than the case when VGS is equal to 0. Okay, not only that, but also the drain current at VDS SAT, or the drain current at pinch off, is much smaller. So it's 3.6 milliamps instead of the previous example when it was 10 milliamps. So let us, in this case, plot the IV curve for this JFET for different VGS values. So similar to the BJT, increasing IB results in an increase in the IC. In this case, increasing VGS results in a decrease in the drain source current. So when VGS is equal to 0, this is the trend. So as you can see, this is a voltage controlled device as opposed to a current control device, but increasing VGS results in a smaller amount of IDS. And notice also this non-linear relationship here. Notice the non-linear relationship between VDS. See, notice the non-linear relationship between VDS and VGS. Notice the non-linear relationship between VDS and VGS. So there is this nice video that you can see, and this video, it kind of explains, or it kind of shows some parallels, analogies between a JFET and a faucet. Okay, a faucet, this is where you get some water. So I would encourage you to have a look at this video. It explains how the JFET works, very similar to a water faucet. So now some important mathematical expressions. So first of all, VDS SAT, this is equal to the pinch off voltage VP plus VGS. Also, the drain current is approximately equal to VDS SAT over the resistance between points A and P, pinch off point. This is for VGS. So we know that VDS SAT is equal to VP plus VGS. So if we do this replacement, then as a result, the drain current is equal to this expression. Remember that VGS is a negative voltage, right? Beyond pinch off, so when VDS is much greater than VDS SAT, the point P, where the channel is just pinched off, still remains at potential VDS SAT, given by the above expression. So the resistance increases with more negative gate voltage, as this increases the reverse bias across the PN junction, which leads to a narrowing of the channel. So when VGS is minus 4 volts, the channel thickness at A becomes narrower than in the case when VGS is equal to minus 2 volts, okay? So increasing the resistance RAP of the conduction channel, and therefore it also decreases IDS. Moreover, there is a reduction in the drain current as a result of VDS decreasing with negative VGS. So the figure in the slide that I previously showed shows the effect of the gate voltage on ID versus VDS behavior. These two effects, i.e. from VDS SAT and that from the resistance between the points A and P in the channel, they lead to IDS almost decreasing parabolically with a negative VGS. This parabolic behavior. Obviously, the channel can be completely switched off with a high voltage. So in this case, if VGS is equal to the pinch off voltage minus 5 volts, then the channel is said to be off. The two depletion layers, they touch each other, they completely block the channel, and as a result, there is no current that can flow between the drain and the source. So when VGS is minus 5 volts, the depletion layers, they close the whole channel from the start, and VDS is equal to 0. And as VDS is increased, there is very small drain current, which is a small reverse leakage current due to thermal generation of carriers in the depletion layers. Okay, I can see that the bell has already went. So let us take a break for a few minutes and then we will come back and resume the lectures. Okay, so welcome back, everyone. Let us just resume. So we stopped off at the JFET characteristics. So now let's look at the transfer characteristics of a JFET. So starting off with the ID versus the IDS versus VGS characteristics. And as we discussed, increasing VGS results in a nonlinear decrease in IDS. And we will look at the typical formula, the typical quadratic formula that is used to describe this behavior. So gradually increasing VGS results in this gradual decrease in IDS until we reach the pinch-off point where there is no further increase, where there is no further current taking place between the drain and the source. This is also how we typically connect our JFET. So the terminals of the gate and the source, they're connected in this way, right? And then at the output, the drain and the source, they are connected in this particular way. And for this, the VGS voltage. So what happens at the input circuit, this controls what happens at the output circuit. So the VGS controls what happens at the output. And this is why this is called a voltage controlled device. So one way to describe the relationship between IDS and VGS is via this expression here. So this expression is used in order to define the relationship between IDS and VGS. Okay, so as a result, increasing VGS results in a decrease in IDS. IDSS, this is the drain current, this is the saturation drain current when VGS is equal to 0. VGS off, this is the pinch-off voltage. This is the pinch-off voltage. This is the gate source voltage that is required in order to cause pinch-off. So there are two important facts to note about JFETs. The first is that modulating the electric field in the reverse biased depletion layer by change of VGS, this varies the depletion layer penetration into the channel, and it also varies the resistance in the channel. So the transistor action in this case can be thought of as being a field effect. Since there is a p-n junction between the gate and the channel, this is why we have this name AJFET. The second important fact about JFETs is that the region between the pinch-off is commonly known as the current saturation region, as well as the constant current region and the pentode region. The term saturation should not be confused with similar terms that are used for bipolar transistors. So a saturated BJT cannot be used as an amplifier, but the JFET is used as an amplifier in the saturation current region. Okay? So just be careful with the terms saturated. You will come across also the term saturation region for the MOSFET. So the saturation region for a MOSFET or a BJT and for JFETs, just be careful that you understand the differences between these three regions because they are different for those three types of transistors. So the JFET can be used as an amplifier. In this case, this would be used as a common source amplifier. Please remind yourselves of how the BJT is used as an amplifier. So the transistor action in the JFET, this is controlled by IDS. This means that we are controlling IDS using VGS. Okay, so the transistor, the JFET in this case, the current IDS is controlled by VGS. And the input circuit is the gate source circuit, which contains VGS. And the output circuit is the drain source circuit, which contains the drain current IDS. The JFET is never used in the forward biased region. So VGS is never greater than 0, right? So VGS is always negative biased. Since VGS is always a negative voltage, the maximum current in the output circuit can only be IDSS. So this is the maximum current. right? So the maximum current is when VGS is equal to 0. And since VGS is a negative voltage, so the maximum output current is IDSS, the saturation current IDS. The maximum input voltage VGS should therefore give an IDS less than IDSS. So as a result of increasing, so this is just for you, as a result of increasing this reverse bias voltage VGS, what should happen is that IDS should continuously decrease beyond IDSS, right? So increasing VGS should result in a current IDS that is lower than IDSS. So let's look at an example of where the JFET is used as a common source amplifier. Okay, so let us assume that our JFET is connected in this particular way. So here we have a resistor that is connected to the output, right? And here we are trying to measure the drain current IDS that flows in the output circuit. We also have VGS, okay? And what we want to do is we want to amplify a small input signal, a small AC input signal. So we want to observe what happens to this small AC input signal that is applied at the input. So in the common source amplifier, the input and the output circuits are connected to the same source. So this should say source. So both the input and the output circuits are connected to the same source. This is why it's called a common source amplifier. Now, let us see what happens. So now we know that we understand this behavior between VGS and IDS. So we have this behavior between VGS and IDS. Increasing VGS results in a decrease in IDS, this nonlinear relationship. And we said that this nonlinear relationship can be determined using the previous expression that we saw over here, this expression here. So by knowing what IDSS is, the maximum drain source current, this is when VGS is equal to 0. If we know what the pinch off voltage is, so let's say this is 5 volts, let's say this is 10 milliamps. So by increasing VGS, we can determine the IDS versus VGS relationship. And we can plot this curve. So once we have this curve over here, now for a particular VGS value, let us say that this VGS value is equal to Q, this quiescent point here. So in this case, we are applying a particular voltage, particular VGS voltage. In this case, this is minus 1.5 volts. So we are assuming that we have minus 1.5 volts. So here this is minus 1, this is minus 1.5, as we can see from this example. Now what happens to this input signal? This input signal, this input AC signal, has this type of behavior. Now, as this input signal is introduced into our circuit, what happens at the output? Look at what happens at the output. Because of this particular amplifier, we have amplified the signal, we have amplified this input signal, and we have achieved this output signal over here. Right? So we have amplified this input signal. This input signal is a sinusoidal signal between minus 0.5 and plus 0.5 volts. But this small AC signal has now been amplified to this output signal over here. Let's have a look at some of the numbers. So let us have a look at some of the numbers. So starting off with VGS is equal to 0. So when VGS is equal to 0, so what is VGS? So we know that VGS in this case is minus 1.5 volts. So what is IDS? Let us start doing some calculations. Okay, so what is IDS in this case? what is ID, and let us, we can continue with this example. So let us input in this expression what is IDS, what is VGS, and what is VGS off. So VGS in this case is minus 1.5 volts. VGS is equal to minus 1.5 volts. Okay, so we can continue with this example. IDS is 4.9 milliamps. So what is ID? So remember that ID is equal to delta IDS, the change in IDS. And in this case, the change in IDS is equal to 0. So what is VDS? VDS here is VDD minus IDS RD. VDS over here is VDD minus IDS times RD. So IDS is 4.9, so 4.9 times this resistance RD. And we are assuming that RD is 2 kilo ohms. So we can immediately calculate what is VDS. So this is 8.2 volts. Okay, so far we are in this quiescent region. Now what happens when we start to have points A and B? So now when VGS is minus 0.5 volts, what is VGS? So VGS is now minus 1.5 minus 1.5, so that's minus 2 volts. What is our new IDS value? So let's input our new IDS value into this expression. So now let us input our new IDS value into this expression, and let us find out what is our new IDS value. So a new VGS value, let us find out what is our new IDS value. And if we do this, then we should obtain 3.6 milliamps. So the change in IDS, as you can see, is minus 1.3. So from here to here, the change in IDS is minus 1.3. And because of this change in IDS, we can now determine what is our new VDS. So VDD minus IDS times RD. So we multiply this value, 1.3, by the 2 kilo ohms, and we can immediately see that VDS is increased now to 10.8 volts. So the VDS here, small signal VDS here at this output, is now 2.6. So we've jumped from 8.2 to 10.8. So what is the voltage gain? So what is the voltage gain? We can calculate what the voltage gain is. So this is now point A. We repeat the same procedure now for point B. So for point B, in this case, the most positive point of VGS is 0.5, and we repeat the same process. And as you can see, there is a small difference in the voltage gain. There is an asymmetric relationship between IDS and VGS. This is why we have this small difference in the voltage gain. It's a small, but still a noticeable difference in the voltage gain. Right? And we can determine, as I mentioned, we can determine what IDS is from this expression here for each new VGS value. So please go through this example. Try to understand how our JFET works as a result of these changes in the voltages. So how do we calculate the gain? So the gain is the change in VDS over the change in VGS. Okay, so for the particular example, when we were dealing with this example, so it's the change in VGS divided by the change in VDS divided by the change in VGS. Okay. So the JFET operating as an amplifier, so the amplification can be increased by increasing RD, the resistance, but we must maintain VDS at all times above VDS SAT, i.e. beyond pinch off, to ensure that the drain current IDS in the output circuit is only controlled by VGS in the input circuit. When the signals are small, about DC values, we can use differentials to represent small signals. So for example, small VGS means a change in big VGS. Also, small ID is a change in IDS, and so on. The variation in IDS due to VGS, so the variation in IDS due to VGS about the DC value, may be used to define what is known as the mutual transconductance, GM, for the JFET. The mutual transconductance. And the mutual transconductance is this change in IDS over the change in VGS. So we write it as ID over, so small ID over small VGS. This is called the transconductance. Since we already know what IDS and VDS are, we can substitute and we can differentiate. So GM is equal to minus, so if we have our previous expression, so it's equal to minus 2 times IDSS multiplied by IDS all to the power of half over VGS off. So this is our transconductance, our small signal transconductance. And the small signal gain, so we know that the small signal gain is the change in VDS over the change in VGS. So we know what VDS is, it's equal to minus RD times ID. So we can therefore write the gain as, we already know what ID is from the previous expression over here. So we substitute it into here. And as a result, the gain is equal to minus GM times RD. So as you can see, we can increase the gain by increasing the resistance at the output. And this also shows you the relationship between the gain and the transconductance. So the negative sign, this indicates that the output and the input voltages are out of phase by 180 degrees. This is why there is a negative sign. It shows that the input and the output voltage, they're out of phase by 180 degrees. So let us do this example with each other, please, because this provides a summary of what we have done. So in this particular example, we have an N-channel JFET, common source amplifier. The JFET has an IDSS of 10 milliamps. It has a pinch-off voltage of 5 volts, as we can see over here. The gate DC bias voltage VGG is minus 1.5 volts. The drain supply voltage VDD is 18 volts. And the output resistance is 2 kilo ohms. What is the voltage amplification for small signals? And how does this compare to the peak-to-peak amplification of minus 5.6 found for an input signal that had a peak-to-peak value of 1 volt? So let's just spend 5 minutes thinking about this, and then we will go through it with each other, please. Can my GTAs please make sure that the students are going through this example? Can you please just move around the classroom to see whether everyone is going through this example? Okay, so let's go through this example with each other. So so we are given, we are told that VGS is equal to minus 1.5 volts, right? We are also told that VGS off, or the pinch-off voltage is minus 5 volts. So let us write these things first. So we have VGS equals minus VP equals minus 5 volts. Okay, so that's the first thing that we have. We know from our previous slides that IDS equals IDSS times 1 minus VGS over VGS off all squared. So let us start to substitute some values. We also have IDSS is 10 milliamps. So IDSS equals 10 milliamps. So let us start substituting these values. So we have 10 milliamps, 1 minus VGS. So VGS is minus 1.5 divided by minus 5 all squared. So if we do this calculation, we should achieve something like 4.9 milliamps. Right? So we now have IDS is equal to 4.9 milliamps. So what is the next step? We need to find the voltage amplification for the small signal. So we need to find voltage amplification. So we know that gain AV is equal to minus GM times RD. We have RD, we know that this is 2 kilo ohms, but we don't know what GM is. So let us calculate GM. So GM equals minus 2 times IDSS times IDS square root over VGS off. So if we do the substitution, so this is minus 2 times IDSS is 10 milliamps times 4.9 milliamps over VGS off, which is minus 5. So if we do the calculations, we should get 2.8 times 10 to the minus 3 amps per volt. So this is our transconductance. So now we can go back and calculate what AV is. Therefore, AV equals minus 2.8 times 10 to the minus 3 times 2 times 10 to the 3. So this equals minus 5.6. Okay, so the gain is minus 5.6. So now we have found out what the voltage amplification for the small signal is. We have done that now. The next part is, how does this compare with the peak-to-peak voltage amplification of 5.6 found for an input signal that had a peak-to-peak value of 1? So 5.6, 5.6. So the answer to this is, it is the same. That's it. And that's the answer to the question. It is the same. Okay, so that is our example here. So I've left here some blank slides for you to do the solution. Let's look at another example together, please. So here we have an N-channel JFET. It has a pinch-off voltage of 5 volts, an IDSS of 10 milliamps. Again, it is used as a common source configuration, and the gate-to-source bias voltage VGS is minus 1.5 volts. Suppose that VDD is 25 volts. VDD is 25 volts. If a small signal voltage gain of minus 10 is needed, what should be the drain resistance RD, and what is the VDS value? Okay, so this needs a bit of thinking. What is the drain resistance RD and what is VDS? So please have a think. And let's do this example again with each other. Okay. So let's try to do this part first. So we are given VP. So VP is 5 volts. We are given IDS. This is 10 milliamps. And we are told that VGS is equal to VGG equals minus 1.5. Okay, so these are our givens. And we are told to find out if we want a gain of 10. So we want a gain of 10. What should be the drain resistance RD? So first of all, we know that IDS, again from our expression, is equal to IDSS times 1 minus VGS over minus VP, all to the power of 2. So if we do the substitutions, so 10 milliamps, 1 minus, VGS is 1 minus 1.5 volts over 5 whole squared. And so this gives us again 4.9 milliamps. Okay. So what is the transconductance? We know that the gain AV is equal to minus GM times RD. We want to find out what RD is. We know what the gain is. So the gain we are told is minus 10. We need to find RD. So the best thing to do is to find out what GM is. So by finding GM, we can then determine what RD is. So what is GM? So therefore GM is equal to 2 times IDS over VP times 1 minus VGS over minus VP. So that is minus 2. I'm sorry, I think I've forgotten a minus here. So this is minus 2 times 10 milliamps over 5 times 1 minus 1.5 minus 5. So this is minus 2.8 times 10 to the minus 3 amps per volt. Therefore, RD is equal to AV over minus GM. So AV we said is 10. GM is 2.8 times 10 to the minus 3. So R is equal to 3.5, approximately 3.5 kilo ohms. Next part involves finding out what VDS is. So next part involves finding out what VDS is. So we know that VDS equals VDD minus IDS times RD. So we are told what VDD is 25 volts minus IDS, so that is 4.9 times 10 to the minus 3 times RD. So we've just calculated it. It's approximately equal to 3,500. So I think it's 3,500 and some, let's say it's 3,500. So that is approximately equal to around 7.5 volts. So VDS is approximately equal to 7.5 volts. And you can verify that in your own time. So here we have found out what RD is, and we have found out what VDS is. The next part, finding out part B. So if an AC signal of 1 volt peak to peak is applied to the gate in series with the DC bias voltage, what will the AC output voltage peak to peak be? What is the voltage gain for positive and negative input signals, and what is your conclusion? So part B. So I think part B will take a bit more time. I don't think we'll be able to complete part B all today, but I want you to think about it and prepare for our next lecture. So just before our next lecture, as I mentioned, please make sure to bring a connected device because we will do some exercises together as a group. But before we do that, we will go through this particular example, part B. We'll finish off part B. So that's all for today's lecture. That's all I have to say for today's lecture. If you have any questions, I'm available at the very end. So thank you very much for your attention. See you next week.
Hello, Professor.
Yes, hello.
Could you please upload the Word form of the lab to the Moodle because the PDF file we cannot modify it.
You would like to have the Word file?
We need the Word form of the lab to requirement to modify the lab.
Okay.
Please upload that and great thanks.
Okay, thank you.
Thank you.
Hi, Professor Gang. I asked some students asked me whether this can see this equation. Someone think that this equation might be wrong. I think this is not VDS, but it should be VGD, right? This equation can see everything 13 page.
This one here?
13 page 13. Yeah, this one. VDS saturation equals VGS minus. I think it should be the. It should be VGD one.
Maybe it should be, sorry? So this is a mistake in the notes. This is a mistake in the notes. This should be VGD. This should be VGD. So this is a typing error in the notes. I will make sure to correct this before when uploading the lecture notes. So this is a typing mistake. So this is VGS minus VGD, and at pitch off, VGD at pinch off is equal to minus VP. That's why we have this. So this is a typing mistake. Thank you very much for pointing that out. I'll make sure to correct this in the lecture notes. Thank you very much for pointing that out. Thank you. Thank you. I will upload this to Moodle. So this is a typing mistake. So this should be VGS minus VGD, and at VGD is equal to minus VP, which is why we replace this over here. So it appears as VGS plus VP. Okay. Thank you very much.
因为还有谁想问问题问啊？我要说，还有让你。I think there's no further questions for today's lecture.
Okay, thank you so much. So looking forward to seeing you next week. Thank you very much.
Thank you. So we will end.
Okay, bye-bye. Thank you.